Yeah, so welcome back to Economics YouTube channel. This is our second class on calculus of variation. Yeah, so we have a different kind of question, the same process, and I have decided to, work on this question because I find it interesting. Okay, right. So how do we go about it? So we have to optimize that particular function over there, subject to this. Here we don't have any value for time. So how do we solve? I kind of think this is even easier. Or so here a functional is what is inside the integral. So we have 3x dot squared divided by 8t cubed. So we find our fx. So f um, x here. If you look at it, there is no x in this place, right? So fx is just 0. All right. Then we look for f x, the one with the dots. Okay. So in this kind of a thing, you have it here. What is below is assumed to be a constant, so it still stays there. So we'll be having 6x dots divided by 8 to the power 3. So we can just divide both sides by 2. So we have 3x dots over 4t raised to power 3. So we then substitute into the Jonas equation, substituting into uh, equation. So, and if you remember the formula, it says your df dx equals d dt of your df dx dots. So, in other words, this is just saying that your f of x is equal to your d dt of your f of x dots. So that's what it's saying. So you can just write it that way. So f of x, if you look at it, f of x is 0. So you have 0 equals um, d dt of 3x dot over 40 raised to power 3. Interesting. So normally, what we are supposed to do is to differentiate this guy with respect to time. The example that we treated first didn't have any element of time, so just an element of x dot, if I can recall properly. So, but if you look at this, so I just present us with a tough time because remember that x on its own, x dot on its own is the x dt. Alright, so you have kind of inside this x dot, there's an element of time, then you also have time standing here. But the thing is that the problem has been made easier because f of x is 0. You understand? So like what I'm trying to say is normally what would have done is we differentiate this guy, you get a result. After getting that result, we then integrate the result. Okay, for us to be able to get x alone. Okay, for example, now let's say we are able to successfully differentiate this guy. So x is going to be dot dot x like double points on it. So we have to then integrate it 2 times. Understand? In order to be able to get x, you know, and to be integrates on both sides. But the thing here is that we can just integrate right away because even if we differentiate this guy first, this is already 0. Understand? So it's still going to be equal to 0. So which means that there's no much of a point. So straight up integrate both sides. So we have integral of 0 dt equals to integral of d dt and 3x dot over 4t cubed. So what happens is integral of this one just becomes a constant. That's what's going to give us constant. Okay, so we have c1, right? Yeah, c1 equals to, now the integral cancels the differential. The integral here cancels the differential, so we are just left with 3x dot over 4t raised power 3. Okay, so from here, 3x dot is equal to 4t raised power 3 c1. Okay, so now we can also integrate again in order to be able to get just x. All right, so integral 3x dt equals to integral 4 t raised power 3 c1 dt. So when we do this, this is just going to be 3x, right, equals to, we have 4 t raised power 3 divided by 4 c1, then plus c2. Yeah, plus c2. So let me verify, let's know what we're doing. All right, wait. This is t, this plus 1. So 3 plus 1, so it's, I believe you understand what I did there. So 3x equals to 2 t raised power 4 c1 plus c2. All right, so from here, then x equals 1 over 3, or I can just say c1 over 3 t raised power 4 plus c2 over 3. All right, so that's why I said this one is even kind of easier. So we are done. We can't substitute x0, x1 simply because all we're given was just this. And whenever you're given something like this is where your answer is going to be to end. You can't find c1 and c2. There's nothing you're going to do about that. So c1 over 3. All right, now what about the sufficiency condition? So our f here, fx is 0. So you have fx equals 0. So definitely fxx is 0, and fx x dot, this is 0. So everything is just 0. Then our fx dot is 3. So fx dot is equal to 6. Okay, let me just use 3. 3 x dot over 4t3. So fxx will be equal to 3. Yeah, so this guy disappears. So we have 3 over 4 c3. So okay, so now at the end of the day, d, okay, should I write it? Let's just manage here. So our d at the end of the day is, you have fxx, this guy, 0. Then you have xxx dot, this guy, 0. You have fx dot x, which is still this guy when you rearrange it, 0. Then, so fx dot is that. So we have 3 over 4 c3. Of course, the worst thing that can happen is for t to be 0. And if t is 0, so the whole thing becomes 0. All right, so in this particular case, we can say that the sufficiency condition have d1 equals to 0, then our d2 equals d is also equal to 0. This times this minus this times this, everything is 0. So in this case, what we do is to rearrange. So when we rearrange, so the second d was going to be starting with 3 over 4 c cube 0 0 0. Alright, so here d1 will be equal to 3 over 4 c cube, then d2 equals D be equal to 0. So at the end of the day, this is positive, right? So we have D1, being greater or equal to 0 at the end of the day, and then we have D2 equal to D, okay, greater or equal to 0. So I didn't clean this part. So if you look at it, it fulfills um, the local minimum, condition. So it's just like the other result that we got in the very first video that we did. So if you look at it, we've tested it for all possible orderings, the two orderings. So D is positive semi-definite. Okay, the conclusion for that, D is positive, since we have this result, D is positive semi-definite, and F is simply convex, which is sufficient for a local minimum. So we've been able to solve this question. So the next that you'll be getting is an assignment on this. So you can have your question in different format, just calm down, the process is the same. You understand? So I would encourage you to solve as many questions as you can, lay your hands on. Okay, they are still within the range of what we've done. So the format, the logic, everything is the same. All right. So some questions have exponential equations in them. You still kind of, so just look for them. Just solve left and right, and it'll be great. But it's a simple thing. Generally, the assignment says maximize that function x dot squared plus 40t is per 3x dt subject to x t naught equals x0 x1 equals x1. All right, so your upper bound, your lower bound, they are there. So just kind of the same um, logic. All right, the same logic, and you're going to be all right. So it does be carried away by the word maximize here. So eventually it might be having a minimum, a maximum, it might be maximized, it might be optimized, whatever it is. Just make sure that you do your work correctly. So I think with that, we are done with the calculus of variation. Like I promised, like I mentioned in the last class. So the next now we are going into now is optimal control theorem. It's kind of similar to this, but you know, see you there. Yeah, see you there.